The next presentation is by Dr. Hyun Kil Shin, Korea Institute of Toxicology, South Korea. And the presentation is on beyond structural diversity of organic molecules, electron configuration, fingerprint of inorganic bulk materials, and engineered nanomaterials. Hyun Kil, can you unmute yourself? And you can share your screen. Yeah, we can hear you.
Okay.
Can you share your screen?
I'm using my laptop, and sometimes this camera doesn't work, and it's happening now. So that's why you don't see me. I think I should just give a presentation in this,
yes,
like that, yeah.
Yeah, can you just press like slideshow?
Do you see the slide?
Yeah, can you just increase the size of it?
Sorry.
Yeah, it's fine.
Size?
Can you enable your camera?
Wait a second. Let me try. I turn on my camera, but doesn't.
We are unable to view it.
Oh, okay.
Yeah, that's fine now.
Okay. Sorry for the delay. And my name is Hyun Kil Shin from Korea Institute of Toxicology. And the main focus of my research is prediction of toxicity. But it doesn't only consider drug molecules, but it considers all chemicals. And in this presentation, I'd like to introduce my recent research outcomes, which is about electron configuration fingerprint development. And it is designed for inorganic compounds. And the concept is extended for prediction of cytotoxicity of nanomaterials. And at the moment, most of machine learning models for toxicity prediction is only usable for organic molecules, and I start to work to extend their applicability domain for inorganic molecules. So let me start why I focus on inorganic compounds. First of all, in my recent project, I realized that quite a many number of inorganic compounds are used in our environment, maybe in industrial application too. So if you see the figure here below, I collected list of biocides from different sources, one from ICA in Europe, and another from the books, which collected all biocides, and another from Korean government, which regulate the use of biocides. And when I combine all of them, I found out that actually 20% of biocides belong to inorganic compounds. And in Europe and also in Korea, chemicals should be registered, and in the registration, toxicity information or physicochemical properties should be submitted. And due to the cost for measurement of these properties, in silico models can be used. However, these 20% of biocides cannot be predicted with models. So these should be experimented. And I feel that there must be a model that can cover this chemical space. And another reason I work with inorganic compounds is that maybe in silico models for inorganic compounds can provide more opportunity in maybe in drug development too. And at the moment, in silico models for toxicity prediction actually explore on the fraction of periodic table, and there are much more elements that should be studied and that can be used in in the future use. So I believe that inorganic compounds also should be considered in silico modeling studies. And I already mentioned that the most of work I do is called CUSA, which stands for Quantitative Structure Activity Relationship. And most of these CUSA models are applied for organic molecules. And maybe first reason is because of data. Most of data for CUSA modeling is organic molecules. And because of the less number of inorganic molecules, maybe researchers are not quite interested in modeling for inorganic molecules. And maybe the second reason is the lack of cheminformatics tools. QSAR has a history of, it started from 1950, and there are many tools that can calculate features for organic molecules. However, these are not applicable for inorganic compounds. So even though there are 50 or 60 years of studies on QSA modeling, but these cannot be applied for inorganic molecules. So at the moment, lack of cheminformatics tools are quite obstacle in development of QSA model for inorganic compounds. And particularly in model development, calculation of descriptor is quite important, because technically molecular descriptor is by definition mathematical interpretation of chemical structure, but in practical sense, it's numerical values. Any numerical values can be derived from the structure. And there are many types of descriptor, and one different type is called molecular fingerprint, which converts molecular structure into bit string, and it is quite useful method in modeling. And when it comes to inorganic compounds, people use two types of input structure. One is crystal structure, and the other is composition. And in the beginning, I mentioned that I want to develop model for chemical registration for EU ECHA, and then any people can be used the model. They don't need to have profound understanding on crystal structure to register their product. So I want to start with quite simple information, which is composition. And there are two types of descriptor only consider composition of inorganic compounds. One is just counting the number of atoms within inorganic compounds, and the other is called MET minor, which uses physically meaningful descriptors. So currently there are only two descriptors apart from my study. And another issue is in Nanocusa modeling. So nanomaterial and organic molecules have quite different chemical structure. So recently there are different types of modeling for nanomaterials, and we call it Nanocusa. And at the moment, Nanocusa model is developed with quite small number of data, around 20, and they only focus on specific type of nanomaterials. What I mean by that is they developed a model with metal oxide nanoparticles without coating, or they developed a model with quantum dots alone. So at the moment, applicability domain of Nanocusa model is quite narrow. And there is also two reasons. One is data, and another one is descriptor. I explained that in the next slide. And some people developed actually Nanocusa model with quantum mechanical descriptors in order to cover wide range of nanomaterials in their modeling. However, this approach is also quite limited, because in the study, in quantum mechanical calculation, actually particle size cannot be increased as much as the real size of nanomaterial. And another issue is that available crystal structures are quite limited. For example, in coated metal nanoparticle, there are no actually crystal structure for coated metal nanoparticle. So even they should design coating materials alignment without experimental basis. So that's a limitation I found in using QM descriptors in Nanocusa modeling. So I also see that the novel descriptor is required in Nanocusa modeling, and particularly there are a huge gap between complexity. In terms of complexity, when I see the nano material based product, they are actually fabricated with all different compositions in all different sizes. However, in Nanocusa studies, which predict cytotoxicity of nanomaterials, they consider very simple information or just one composition. They use data set with only one single composition or quite limited complexity in their nanostructure. So I want to introduce some more studies about Nanocusa modeling. And the first one is actually they collected all nanomaterial information, experimented for environmental species. And actually their conclusion is that they actually intended to develop Nanocusa model, but they couldn't because of the noise in the dataset. So at the moment, nanomaterials are quite easily aggregated in the media. That's why their characters are quite easily changed. And because of that, researchers who experimented nanomaterials use different types of pre-processing. In here, they use different experimental protocols to scatter nanomaterials in the media. And that actually makes quite difference in the assay outcome. And this left one is my study in 2018. So I just collected carefully curated data set. There is a test guideline for Daphnia magna toxicity screening. So I selected all the articles which follow test guideline. However, still the data was quite erroneous, and they are quite hugely influenced by change of experimental background. And the noise is quite severe than organic molecules assay outcome. So that's why in modeling, I used experimental settings as a variable. And another issue in my study was that I collected actually a wide range of nanomaterials, metal oxide, metals, coated metal, and carbon-based nanomaterials. So I collect entirely like more than 1,000 data points. However, in actual modeling, each model was separately developed for metal oxide, metal, and carbon nanomaterials. So I cannot use, even though I have 1,000 data, but that 1,000 data points cannot be used in model training altogether, but they are separated. And model was separately developed because there was no descriptor that can commonly calculate it from metal oxide and also metal and also carbon. So because of the different set of feature, I had to divide a data set, and model was separately developed. And that's actually quite a loss because all data cannot be used in one model development. So that's a background. And in this presentation, I would like to introduce 3 of my studies. First one is electron configuration. Fingerprint was designed to predict physicochemical properties of inorganic compounds. And based on this study, I extend the concept of electron configuration fingerprint to design size-dependent electron configuration fingerprint for nanomaterials. So these concept was used, and by this fingerprint, actually general model for all types of nanomaterials were developed. And another one is physical-chemical property were used as a descriptor for development of prediction model for biocides, and particularly I developed model for inorganic biocides. So the reason I come up with the concept of electron configuration was actually based on quantum mechanical calculation. Vaguely, quantum mechanical calculation is actually based on, in my understanding, it's based on interaction between electrons and protons. And these interactions were calculated, and if quantum mechanical software, calculation software was used, then based on these interactions, quantum mechanical properties like molecular orbital energies or dipole moments, sort of quantum mechanical properties were calculated, and these quantum mechanical properties, or we can call it quantum mechanical descriptors, were used in model development to predict endpoints such as cytotoxicity. So my idea was that maybe it's also possible that just electrons within molecules, if electrons within molecules were quantified, then this information can be used as a descriptor or like a fingerprint, and to predict endpoints, what I want to predict. And particularly these interactions between electrons can be modeled throughout machine learning during the training of the model. Particularly when I think about the neural network, it calculates all interactions between input. So I had the idea that maybe it's possible, and thus it was used. So electron configuration was used as a fingerprint in model development. So this is the first model I developed. And when I studied all machine learning models or deep learning models for inorganic compounds, they were actually intended for material design. So they predict some parameters important in material synthesis or their properties. And so this is quite first study of physical chemical property prediction for inorganic compounds. And the right side, I presented data set I used. Here you can see the quite wide range of endpoints was covered. For example, for boiling point, which covered, you can see in the table that the range of boiling point was this much wide. And this periodic table shows the diversity of atoms in my data set. And the gray colored atoms are absent in the data set. So if you see the colored atoms, then you can see that most of atoms on the periodic table are covered in the data set. And I developed a model for boiling points, water solubility, and melting point and pyrolysis point prediction. And I developed a model with neural network, and I also compared the model with other models developed with descriptors I introduced in the beginning, NetMiner, and just using atom composition. And the electron configuration fingerprint actually outperformed the other descriptors. And you can see the prediction accuracy here. And I believe it's quite a good prediction accuracy. According to some research articles, R² over 0.6 on external test set is a cutoff to decide whether the model prediction is accurate or not. So in here, formulas actually achieved quite good accuracy. And the properties these 4 neural network models were further used as a descriptor calculation for biocides. In this study, I didn't only develop for inorganic compounds, but also for organic biocides. And the prediction accuracy of the model was compared with other blood-brain barrier permeation prediction model developed for drug-like compounds. And actually this model here actually achieved 10 times higher accuracy compared to models for drug-like compounds. And there's quite different structure diversity in biocides compared to drug-like molecules. And here I present inorganic compounds. So I focus on just inorganic compounds. And unfortunately, there are not many data, but not many low BB data for inorganic compounds. I obtained only 11. So I don't have much option for a machine learning algorithm. So I go with linear model, and I used maximum 2 descriptors because some articles suggested that at least 5 data points are required to decide the coefficients for the descriptor. So I assume that 2 descriptors may be the maximum number of descriptors that can be used in the model. So I use linear model, and actually the data set I found wasn't exactly biocide. The data set I found was it's not exactly biocide, but I can see that some biocides have similar properties with the log BB data set. So I thought that the model developed with log BB data can also be used for inorganic biocides. And due to the small number of data and the small number of descriptors used in the model's applicability domain is quite limited. So some inorganic compounds with higher boiling points or low solubility cannot be reliably predicted. However, if inorganic compounds are within the chemical space, then a prediction result was quite reliable. But still, this model requires thorough examination of applicability domain, whether the input molecule is within the domain or not, unless prediction results are not reliable. And this is the last one. I developed a general model for nanomaterials. So as I mentioned, normally prediction models for nanomaterials were developed for metal oxide or just metal or just coated metals. But here I collected all different types of nanomaterials. So first one is cytotoxicity dataset. And this figure is about the diversity of a coating material. And when you see the zeta potential dataset, actually there are much more diverse nanomaterials were included. So in here, there's a metal oxide, metal and coated metal, and quantum dot, and carbon-based nanomaterials. So in here, what I want to emphasize is that actually model was developed from all different types of nanomaterials, and model achieved quite good prediction accuracy. And another issue in nanotoxicity prediction is that how can we measure the similarity between nanomaterials? Nanomaterials have diverse compositions, and they are different in size. So size should be considered in similarity, or core materials should be used as a similarity measurement between nanomaterials. But in here, the fingerprint I used actually can quantify the amount of electrons within nanomaterials. So based on that information, actually the similarity of nanomaterials can be measured quantitatively. So if you see here the PCA result, the color means the value of the property. So brighter means higher value of higher value, and darker means lower value. And if you see here, quite data points closely located actually have similar colors. There are some exceptions, but mostly they are quite grouped together with similar colors, which means similar values were closely distanced based on this fingerprint. So I assume that this fingerprint can be used in grouping method too. And in toxicity prediction, there's a method called read across, which uses already known experimental value and use it to then apply that value to structurally similar compounds or similar structures. And by using this fingerprint, I think this grouping can be more efficiently performed by numerically measure the distance between nanostructures. So that's the my presentation. So I start to work with inorganic compounds because in silico models are quite limited in their application. They only use for organic molecules. So I come up with the electron configuration fingerprint, and it was used to develop physical chemical property prediction. And this physical chemical property prediction models were used as a descriptor calculator for inorganic biocides. And this concept was extended based on the size of the nanoparticle. So I developed the size-dependent electron configuration fingerprint, which used as a descriptor for nanomaterials. And this concept made it possible to include all different types of nanomaterials in model development. And this can be also used in nanostructure similarity measurement. So that's all. So these are funding information, and all the works are done with my colleagues in my institute. Thanks for your attention, and if you have any question, please share with me. Hello. This is the end of my presentation.
Yes, thank you, Dr. Hyun. Yes, any questions from audience?